Hey, welcome back. Today we're going to be talking about the relationship between torque, work, and kinetic energy, and how do we solve problems using those concepts. So this is primarily for AP Physics C Mechanics students, and let's review some of the major ideas we've been talking about lately. So we know if we're taking a look at statement A up here, if an object has a net torque applied to it, that object is going to gain rotational kinetic energy. We've talked about rotational kinetic energy. It's a thing, and our rotational kinetic energy equation is 1/2 I omega squared. So that is something to think about. We could imagine an object like we have right here. Let's say we've got a torque applied on that object, so this is going to be a force applied at a distance right here to the axis of rotation. So that force is applied at a distance to the axis of rotation at a right angle. Let's just make it easy and say this is a right angle right here. If we do that, then we're talking about a torque. That torque, if you have a net torque, that will change the kinetic energy of the object. So that's effectively doing work, and that's what I want to talk about and think about those relationships today. So we do know our basic kinetic energy equation here in a linear sense. This work equation right here, we can rewrite this in a slightly different format. We could call this dx. This dr, dx business, they're largely interchangeable for these kinds of problems. Can't forget the integral here, and that's one of the concepts we've talked about too, is that if you have a varying force, you can integrate that force function with respect to x, and that will give you the work done on the object by that force. Okay, very good. So then we've also said this is the Work Kinetic Energy Theorem, which helpfully is now on your equation sheet. Didn't used to be on your equation sheet, now it's on there. So the net work applied on an object will change the kinetic energy by the same amount in terms of joules. Or you can look at the individual forces doing their own individual sets of work and do problems related to that as well. So that's all background for what we're saying so far. What we do want to get to is we want to get to this right here. We want to get to this idea that work is equal to a torque d theta. So how do we get there? Let's think about this. Like I said, we have this equation right here where we said work is equal to the integral of f dx. Let's call it dx because, by the way, because it's rotating, it's going to be moving in a circular path. So you want to think of this as like an arc length. So you would say s is equal to an arc length. And it turns out that we do have that equation as well. I'm going to put that in the lower left down here, circle that. This S is our arc length. Now for our purposes here, we can kind of set our arc length equal to X because our arc length is the distance, the X value over which that force is applied. If we're talking about a rotating system like this trapezoid as it rotates, let's assume we have that net force on the corner, on the top corner here. That's going to cause that rotation along the arc length. So let's think about what we can do. We can say, well, this equation could be changed to say x is equal to r times theta. Well, if that's the case, x is equal to r times theta. Let's think about what we could do with that. We could take that and plug that in over here. Instead of dx, we could say, therefore, work is equal to force, and then we will say r d theta. Now we're getting somewhere. Now we're starting to think in a more rotational sense. Now if we assume these are at right angles to each other here, so I'm just going to make it easy. Remember, you could say torque is equal to r crossed with the force, but if they're at 90 degrees, then you could just say torque is equal to rf multiplied by each other if 90 degrees. Okay, well if that's the case, then we can say, we'll just change the order here so you can start to spot what I'm about to say. So if we say r times f times d theta, then it's really not much of a stretch to say this is work is equal to tau, torque, d theta. Over here, the integral of this, I can't forget the integral for all of these. And so we want to take that into account. This is a really important rotational version of something that we've been talking about lately for work done to a system and so on. Alright, now there is a rotational work kinetic energy theorem that we can get to as well. And so I do want to talk you through that briefly. And so if we said work is equal to the integral of tau d theta, well let's assume a constant torque. If we do that, then we can say work is equal to torque and pull this out here, and we just have the integral of d theta. Well, if that's the case, then that is simply saying work is equal to tau times delta theta, because that's what the integral of d theta is, it's delta theta. Well, we did also say torque is equal to I times alpha, right? Well, what if we threw that in here? Then we could further say work is equal to I times alpha times delta theta. Okay, and I am out of room, so I'm going to move this up briefly. And we did say that work is equal to I times alpha times delta theta. And I'm going somewhere with this. I'm going to prove to you a relationship that we're going to need. And so one rotational kinematics equation that we have that we can work with, if we end up isolating for alpha, then we can actually plug that in for alpha and see what happens. Now there's a reason for this. We are going somewhere with this, so bear with me just for a moment. We can say work is equal to I, and then this alpha becomes omega squared minus omega naught squared over 2 delta theta times our delta theta. These delta thetas cancel, and if you think about what we have, we're saying work is equal to 1/2 I times omega final squared minus omega initial squared, and that's just a change in kinetic energy, rotational kinetic energy. That's all it is. So this work is going to be equal to our change in rotational kinetic energy. So effectively we have proven that that is the case. We already know the linear version of this works out, but this is how you could derive it if you had to on the test itself, and how to start to relate all of these ideas in a little deeper level of understanding in your mind. I have done screencasts on an entire year of physics and almost all the concepts for AP Physics C mechanics, so if you have any questions or comments down below, please let me know, and I hope you all have a great day. Take care.